sessions will be dedicated to BSM physics, and we will have a first talk by Caterina Doglioni from Manchester and Lund University, and she will talk about the perspective for in particular dark matter at future colliders. So Caterina, thank you very much. And
thanks to you for the invitation. I'm sorry I'm not actually in Trento. I'm from nearby, so it would have been a nice thing to do.
It would be nice, but
next time.
Unfortunately next time, yeah.
Next time, okay. So yes, thank you very much for the invitation. I'm going to talk about BSM at Future Collider for about 45 minutes to an hour, and then we should have some discussion, which I think we can take either on Zoom or maybe on Gather Time, what people prefer. And I will not probably not see the chat, so if someone has questions, please interrupt me. There's not enough of us to disrupt the flow anyway. So let's go for what I'm going to talk about. I will first introduce questions and tools, why we're doing this, why we're looking for standard model, and then try to convince you that we don't need to have standard model problems to look for beyond the standard model, but we do have problems in the standard model, and we more or less all know what they are. So we may have some, we definitely have some others. And in particular, one that I will talk about in more detail is dark matter, with some experimental considerations surrounding the design of data taking strategies for future colliders. And then I conclude with some ideas on synergies with complementary experiments and things that are going on, and then conclude. So of course, this is not an exhaustive talk on all BSM physics. There's a long list of things that I've omitted. And I've privileged my favorite thing, which is hadronic jets. So you'll see a lot of jet things in there. And there was the Energy Frontier Restart workshop last week. So a number of slides are coming from there, or ideas are coming from there. And since I'm involved in that as a topical group convener of the dark matter colliders, but if you need or you see your studies included in this, let me know. So let's start with the introduction. This is something that we've already seen on Monday on the landscape for future colliders. So there's a number of E+, E- colliders ranging from the smaller to the bigger. So there's linear colliders, there's circular colliders. The center of mass energy in GeV you can see goes from about 91, that is you want to produce a lot of Z, so it would be a Z factory to begin with, to 3 TeV if, and this is something that is a bit more in the future for with the possibility of a linear collider called click. And the luminosity is somehow inversely proportional to an extent to the, not always though, but depends on the circular or the linear, but you'll see that it's harder to get a lot of luminosity for colliders, for electron-positron colliders with more that have more center of mass energy, and this is just due to the properties of the collider. So there's a bit of a trade-off there in terms of electron-positron colliders. You can also go for other kinds of lepton colliders on a much longer timescale, and this is something that everyone loves. It's muon colliders. It's a new kind of circular colliders where the technology is still very much in development. Where you can go from 30 to 30 TeV. Sorry, the instantaneous luminosity is gone missing, but you could get up to 2 attobarn of that of integrated luminosity at an energy that is very high, so something that no other lepton collider can reach. But with the advantage of electron-positron colliders, that is a cleaner environment with respect to proton-proton colliders. So if you want to go for proton-proton colliders, then you have to, this is something that you have to take the environment, the messier environment of a hadron collider, but you can reach much higher center of mass energies. So you can go from the guaranteed one that we have, that's Illumi LHC, to something that is more in the future, and you see that in the table below, the FCCHH that could be built at CERN with a 100-kilometer tunnel around Geneva using the LHC as an injector. But this is a much longer time scale, 25, 30 years time scale. So that's the tools that we experimentalists would like to give us data. And what does it take for BSM or standard model discovery? I don't know if this is, this was supposed to be an animation, but it's not actually working very much. It was supposed to show the Higgs peak growing, but I think we know how the Higgs peak look like by now. So you need a number of things beyond the particle collider. And the one thing to note is that oh no, you actually see it on your slide. Very good. Many collisions per second, but not all of them are interesting. So only 1 in 10 to the 13 at the LHC contain an interesting event. For example, the Higgs boson. This number goes, the fraction of interesting events decreases if you increase especially at hadron colliders, if you increase the center mass energy. Then you need detectors, complicated as much as you want, millions of readout channels. You need the experimental teams, you need a theory community that, among other things, can provide the background predictions. And we only have all these things at the LHC. That's the current high energy collider. And I would consider the high LUMI LHCs a present to future colliders. So it's going to happen. And the communities are there. A lot of the people will be similar, but maybe one interesting thing to talk about is how we see the future for high LUMI knowledge, the LHC. We will have all the people and all the things and all the interest that we have right now at the LHC for high LUMI as well. We have the funding for it as well. Well, for future colliders, you don't have any of this. You have simulation. I mean, we have some of it, but not to the same scale at the LHC. So for future colliders, we're looking at perspective studies. So the above cannot be taken for granted. And can it be taken for granted in the future? We don't know. The consequence is that, and the caveat for the studies that I'm showing is not every collider study is comparable. So in some cases you have systematics, in some cases you don't have systematics. Most studies make reasonable assumptions, but they also have to say that theory and experiment thresholds usually have different thresholds for reasonable. So we can take these studies at face value, but things might change in the future. So what the landscape for BSM, as seen from current colliders, is that it looks great. The standard model looks great. There is no 3 sigma excess that can face the standard model at the moment. There's a watch list of things. So there's the lepton flavor universality results that we've seen already on Monday, and there's a link on the talk from Alessandro Trecoli. There's muon G -2. Actually, I wrote a slide when the talk was in the morning of, the talk was on Tuesday. There's another thing that is opening up, that's gravitational wave signals and the consequences on colliders. And there's also the occasional LHC excess. Some people think that we are actually too conservative about those. But in any case, this is a very different situation with respect to the LHC restart in 2020, when we thought we'd turn on the collider and see a heap of new physics coming in. So why do we keep doing it 10 years later? And the first reason is that I wouldn't consider measurements and searches 2 different things. You can do both, and we do both. And we do want to extend our understanding of nature. So there was this article a few years ago about the more precise fine structural constant that got everyone excited. And this is basic science as well. So why shouldn't we be excited about alpha strong being determined with a better precision? The second reason is that we could expect unexpected discoveries. It happened in history. This is the years from concept to discovery for a number of particles. So the muon and tau, no one wanted them in the theory, but they came up. This is something that can happen in the future. And the third historical reason, this is a paper by John Ellis that I think everyone cites, where he says, we do not want to encourage big experimental searches for the Higgs boson. Yeah, but we're stubborn and we do it anyway. So these are 3 reasons that somehow drive me to keep doing beyond the standard model physics. Even when we don't need any standard model problems to look for BSM. I really like the intro message from Daniel's talk 2 days ago, actually, that the standard model has no problems according to the LHC measurements so far, because measurements so far agree with theory. But we can still explore the energy frontier as a direct exploration of the unknown, because we could produce new particles. So this is what you do, direct search strategies. And an example of a bread and butter search is digits at future colliders. And you have a hadron collider and you can reach scales of new particles for like 10, 20, 30 TeV. But we're talking about energy frontier in 2 different ways. And we always lump all this kind of future colliders into an energy frontier. But on the other hand, it will be a while before there's a big increase of center mass energy. So we also have to keep thinking about indirect search strategies. that where there's small deviations from the presence of new particles in loops. And I'll give one example of a flavor physics search at the future colliders in the context of the lepton universality, but I'll be mostly leaving this to other talks. I hope this afternoon maybe we'll shed some light on it, because I'm not necessarily an expert in these things. So how do collider manifestations of new phenomena appear? This direct manifestation. You could have bumps over a background. You could have shifts in some distributions, either at the beginning or at the end of the spectrum. These are just examples of the distribution analyzed in searches at ALS and CMS. And you have three main ingredients. You need data, you need a background prediction, and you need a statistical analysis. I'm talking about the first two in the talk, but the third one is not trivial either, because we remember what happened to the hype that surrounded the diphoton excess in, I think it was 2015, that it was really a statistical fluctuation ultimately. But it looked good because it was a search, a classic. It was searching for a resonant excess. So some people have somehow trademarked this thing that's called the bump hunt, where you have a distribution that is smoothly falling. You have a number of events on the y-axis on the background, then a variable that could be the invariant mass of a di-object system on the x-axis. And then new particle manifests like a bump over the background. And in terms of digits, experimentalists are super keen to do these searches. This is something that happened. We were working on this, basically had the paper written ready. 1 month after the first run 2 data came, both Atlas and CMS published on the same day a paper about digit resonances. And this is also interesting because if you increase LHC energy or future collider energy, you have greater discovery potential for new high mass states. And you can play with it yourself in the collider reach tool. And you can see that if you have an object of 2.5 T of collider 1 that has a lower center of mass energy, you can get with the same, you cannot change also the integrated luminosity, but you can get a reach that is 5 TeV at the second collider that has almost twice as much the integrated luminosity. And this scales very nicely with the collider center of mass energy. But it's not all easy, because I think hunting bumps is not necessarily enough. One thinks, okay, this is super easy. You compare data with the smooth QCD inspired fits, or the formulas disappeared. But it's just something that has a component that is like a PDF, 1 minus x, where x is, you can use it, you can have different variables. You can use the MJJ, you can use MJJ over square root of s. And you just fit the distribution. And then if you really fancy, you can compare the data with simulation, but it's mostly a cross-check, because the simulation doesn't have a theoretical and experimental level of understanding that allows you to actually detect very, very small deviations in this smoothly falling distribution. The problem is that we're already finding pitfalls in this. The comparison of data with smooth QCD inspired fit doesn't work all the time. And the first problem is the data taking rates. So high write process data is not always available because there's too much of it. I'll talk more about this later, because that's what I'm very keen on in developing for future colliders. And the second problem that we're having already is that the smoothness of this QCD distribution is a valid assumption of only up to a point, because first of all, there's calibration effects, including the fact that we don't really have a good way to distinguish and calibrate properly quark jets and gluon jets separately. And this is something that has bitten CDF before, because it was there was a bump that appeared and disappeared once these flavor effects were taken into account. And then the second reason is theoretical. We don't know if QCD is smooth at all orders. Maybe, probably, but maybe there's some PDF potential that makes a small deviation from smoothness, and we don't know that. So the solution to the first problem is that, okay, we get more data, we get smarter in how we take the data, but in terms of the fit that we're doing, we can also do a hybrid fit and the NLO comparison background methods from control regions. That's something that is already used by CMS and improves on sensitivity already. One can also use a full comparison of data to next leading order. This is used, done at the LHC. It's been done a couple of times with the MJJ by Atlas and CMS, but also for the chi distribution. That's an angular variable between the two jets. But this is something that is potentially limited by theory precision, not only also experimental precision, but the most limiting factor at the moment is the theory precision, especially on the non-perturbative side of things. And one needs to start a theory and experimental dialogue on fiducial cuts that are needed, because otherwise we end up searching in a phase space that is not safe for theoretical measurements. But assuming that we're under ideal conditions, this is the slide that summarizes some studies done by Rob Harris within SNOMAS on a variety of potential collision energies, including a collider in the sea at 500 TeV. Why not? There's also a collider in the moon somewhere in literature, so you can dream. Well, different integrated luminosity, and it's checking the sensitivity to excited quarks at different collider scales. So you can see the curves on the discovery mass on the plot on the bottom, where you have the integrated luminosity on the x-axis, and this is the discovery mass on the y-axis, and then you have the different collider lines, and you see that the luminosity doesn't do too much to the discovery potential, but center of mass energy does, as one was expecting. So if one had like the most, I guess, realistic option for a very high energy collider is FCCHH, that is this 100 TeV line here, and you could get to discover 40 TeV excited quarks, where excited quark can be substituted with your favorite resonance. And this is also something that is reflected in the studies that were done in the European strategy. So you see on the y-axis, this is something that is not necessarily just for jets. It's mostly coming from dilepton resonances, and what the kind of exclusion reach you can have with different colliders. And on the y-axis, it's the coupling, the universal coupling to the fermions, and on the x-axis, you have the mass. And you see that here it's interesting because the FCC region does well that's best for low couplings. But then once you get past a certain mass, then the precision experiments, more precision, I guess, at lepton colliders take over in terms of being able to discover rarer resonances, even if they produce fewer of them. And then another couple of just examples, and on the bottom one is leptoquarks, but there are so many variations of leptoquarks that this is just one of them, where you have again mass versus coupling, and then the scale on the 4 fermion contact interactions. This is something that you don't necessarily get from direct searches. You can get from also indirect searches in deviations on angular distributions. Now, beyond that, then one could think about machine learning powered searches, because if you don't know what you're looking for, then maybe you should change your mindset. And this is something that is a bit controversial at the moment, because we've used to search something beyond the standard model, but rather than learning directly from data. So are we victim of our success? Because the standard model works very well. So if we keep looking around it, then maybe we're missing something. So outlier detection is a possibility. So you still use the standard model as a baseline, but you don't necessarily, you look for something that is different from the bulk of the data and assume the standard model is the bulk of the data. Now you can see a number of pitfalls, and we can talk about that in Gather Town or in front of a drink or something, because it's, I think it's quite far from, it's there, it's starting, but it's quite far from getting actually ready to be in production. But there's testing control conditions, like what they did in the LHC Olympics. So they took essentially resonances, and they tried to employ a number of this kind of anomaly detection or outlier detection or unsupervised searches in machine learning to try and detect them. And it's the goal was to learn directly from data, injecting as little bias as possible. And if you read the final report, it's that the consequences are that we're not actually yet there. We can find things that we more or less know about, but not the things that we really don't know about. So we need to improve here. And it's related, it's also very important to reuse LHC data, because maybe we are not thinking about, we haven't thought about the theory that actually is realized in nature when we do the search. So we need to reinterpret, recast, fit, combine, use precision measurements. And it's really an important point to keep in mind, that the data needs to be preserved and the analysis needs to be preserved and possibly even modified. So what do we do in absence of excesses? So if you look, I think maybe Google knows too much about the kind of underlying LHC depression. Is the LHC a failure? I mean, are we thinking about that? Well, I'm not, but still. My feeling about future collider physics that we should keep looking, because we also have new physics that could still manifest in deviations to precisions and the rare and unusual processes. So this is an inspirational slide that I picked from one of the talks at the Energy Frontier Restart workshop, where it just shows the example, an example of rare B decays of how you can get information about new physics through indirect probes. And you can measure a constant, you can calculate precisely the standard model contribution, and then get more information from extra, whatever's on top of it, information of new physics, coupling, and scale. And this is something that if you see an anomaly at low energy, you can actually establish a new scale in particle physics. So if you're really sure about your anomaly, then that becomes an all-loose theorem for a new collider. And but one has to be careful about the calculate precisely standard model contribution part. And this plot is something that was shown in the talk that was quite interesting. So that's the x-axis is the significance of an anomaly, and the y-axis is the relevance of hadronic effect. So more relevant is on the bottom. So you have to be careful about what you're doing on the bottom side, what you call the orange term or what you call the black term here. And this is a very short outlook on the results that everyone's talking about. So G-2 could guarantee to see something at a muon collider, RK and RK star and all the related ones. This to systematically explore the new physics models that explain that require a 100 TeV collider, because the scale of new physics that this point to is around 100 TeV. While if RD and RD star, then if this is actually an anomaly that lasts, then new physics should be around the corner. All right, so finishing up on the problems that we didn't know if we had. Now, standard model problems that we may actually have are of two kinds, according to Murayama, at least. Sorry, the link is gone. I'll fix it later. There's a statical problem with the standard model, so everything that requires that tells you that the theory is not as beautiful as you'd like. So fine-tuning, difference in scalar forces, free standard model parameters. There's also empirical problems, so things that we actually see, but we don't explain using the standard model. We don't want to prioritize as experimentalists, but in Raman Sandron's words, what is plausible plays a big role in making efforts to make discoveries. And there's nothing wrong with looking for the empirical problems, but you can also be informed by considerations of naturalness. What we collider enthusiasts like is that many answers for both these kind of problems can lie in the TeV scale. And one solution that is very popular in theory is supersymmetry, where you actually look for something that is generally an increase of signal in the tail of the distributions of the energy of the system, which could be visible or invisible. And in this sense, if you're looking at the invisible energy, you have to think about everything else that is going on in the event. So a higher collider energy at PP gives you more missing transverse energy, or missing transverse momentum more exactly. But if you're in a cleaner environment, you get better and more precise determination of the invisible energy in the system. So this is what leads to opportunities and challenges that are of different sorts for hadron and lepton colliders. The hadron colliders, yes, have the best reach to discovery of high mass states, but there's challenges like the online data taking thresholds. So because your missing transverse momentum has a lot of different contributions, you can't record as many events as you'd like at low missing transverse momentum. So in the end, your discovery thresholds, for example, for Higgs to invisible, changes with your minimum threshold. And if you're not able to record all the events that you'd like, then your discovery threshold goes up. In terms of, this is the upper limit actually, rather than discovery threshold. And then this is just an example of what kind of, the main issue is the QCD pileup in Higgs to invisible compared to Z to invisible. You really have to do something about simultaneous collision if you're looking at a hadron collider. For electron-positron colliders, they are limited by central mass energy, and the fact that you don't really have a strong coupling to produce new states, but the environment is cleaner. This is an electron-positron collider. We'll see later that muon colliders are a bit different. And there's lower background, so you can probe lower masses or save the data and look for other things at the later stage. And the specific strength is that there's clear tagging. So if you have recoil signatures, then that's a lot better than doing it here. It also gets better results at even compared to the same center to higher center of mass energy colliders. And you can use the beam polarization to help identify the signal or enhance the signal. So here's a number of lines about supersymmetry that come from the European strategy briefing book, and there is discussion is NOMAS on how to improve on these plots. The moment the Gluino projection, you see that they go from a number of TeV to 10 TeV to even more like 20 TeV when you're looking at certain processes in FCCHH, and similar things happen for the squarks. And you can link this, what is the most natural thing or the least natural thing that you can tolerate in the theory. So there's also this idea of having a fine-tuning parameter that gives you how natural your flavor of SUSY is. And this is something that I'd leave for discussion. What is this target? Is this a moving target? We used to say, well, if we find the gluinos at 1 TeV, if we don't find them, the natural SUSY is not worth looking at, then it's 2, then it's 10. But should we actually remove this idea of having a target there? And then you see the same thing for the top quark projections. And you can look at Higgs BSM. This is super broad strokes because there's a lot of things done. There's a lot of articles written as well. But one of the interesting things is the self-couplings of the Higgs, and that's one of the golden targets for future colliders. Because with the self-couplings, you confirm the standard model nature of the Higgs boson, but you also can observe enhancements and new particles decaying to di-Higgs or other loop processes. So having a good handle on the self-couplings means that you can both test the standard model and discover new physics. And these are the sensitivity bounds for the standard model value of the Higgs self-coupling. So you want it to be as small as possible. And you can get to the best results are given by the FCC scenario at the moment. And these are the numbers that you get the numbers in here in the legend. You can also look at another new Higgs-like states like new scalars or compositeness of the Higgs. And again, sorry, the plots I have to go quite fast on the plots, but you can find all the information in the European strategy briefing book. So the top left plots are the ones about the possible new states for a heavy scalar singlet that mixes with the standard model Higgs on the left-hand side. And if it doesn't mix with the Higgs, and there's connections to electroweak phase transitions. And for this, there's a nice reference in Julia's talk on Monday. And then on the bottom is the limit on the scale of the compositeness of the Higgs. So a more powerful collider is the one that, for this kind of signature, is the one that gives you a higher composite scale, so that if it's lower than that, you could discover it. And you also can have Higgs portals, where you have Higgs to invisible constraints that interpret as the Higgs is the portal to dark matter. And here we can see later what this means for dark matter searches. And again, the best upper bound you find at the FCC in the FCC scenarios. Now moving on to the next part of the talk, that is what kind of standard model problems we definitely have is dark matter. And you probably have already heard of the WIMP miracle. So this is a bit of a comedy part that I need half an hour to talk to keep you awake. So we know that dark matter constitutes most of the matter in the universe, and there's also dark energy. And we can use this relic density as a guide. And there's many caveats on what this relic density is and how you get to it. And Julia's talk also had some pointers to it. If you want to explain this relic density with only one new particle that interacts only weakly with no matter and with mass in the range of current experiments, so a WIMP, you can make fun of theorists because you assume it's basically assuming a spherical cow of uniform density looking at the standard model. The complexity of the standard model, and then you say 5 times the matter is just made of one particle. How do you believe that? Well, we try. And it's a reasonable assumption, because at the beginning you look for things that are more prominent, in the same way that in the standard model we discovered the electron and the proton first, and these are the things that we're made of. So it's not too bad to look for broad strokes first. But anyway, under the WIMP assumptions, we actually could discover dark matter in the next decade. But I do need to make fun of the experimentalists as well, where we got in 2016, we got I think it was a Pine Martin chewing some cables and not having a very good time with it, and setting the LHC off by a couple of weeks. Anyway, let's go back to the serious part of the talk. The relic density is actually a guide that we can use for pointing at what kind of dark matter candidates we want to look for. And the minimal option to make up 100% of the relic density is to add only one particle to the standard model. Maybe a couple if you want to change also the mediator, but you can just factorize standard matter on one side, where you have dark matter that is mediated by a Z-like boson or a Higgs boson. And you get, in order to satisfy the relic density, you need stable TeV scale particles with weak force-sized interactions. So you could discover this at the LHC, and this conveniently appears in models that solve other problems in particle physics, so in supersymmetry. And the experimental advantage here is that we can detect it in different ways, and that's a non-negligible advantage, because you can make complementary discoveries in indirect detection, direct detection, colliders, and astrophysics, where you always have to tie it together with a theory in a theory model. So one of the simplest models of dark matter, but also quite powerful because it's self-consistent and it can be seen by different experiments, is the pure Wino and Higgsino models in SUSY terms. And also there's standalone models of minimal dark matter even outside the SUSY realm. And the line on the x-axis is the mass of this dark matter particle, is the line where the thermal relic is satisfied 100% by this particle. So that's kind of a target. For the Higgsino is about 1 TeV, and for the Wino it's about 3 TeV. And you see that the FCC and CLIC are the ones that could exclude or discover that kind of target. Some more recent news about Wino and Higgsino is this is some from SNOMAS, is the muon collider studies that have been popping up in the last year. You can have different signatures of where you can recoil against visible objects. We'll see more about that later. We can have resonances for the dark matter particle bound states that can be excited and decay, or disappear in tracks. So very strange signatures in the detector, where you see a track at some point it goes away because something has decayed into invisibles. And this is the muon colliders, depending on what kind of characteristics you give to the dark matter particle, can also definitely reach the thermal target. And one of the lessons learned from the studies that we can think about as collider physicists is that the beam background is very significant at muon colliders. So this is what this is the muon distribution, and it's very hard to get rid of it because it is quite high energy at that point with the beam background on. So this is something that the people doing phenomenological studies are trying to take into account in the best possible ways. But in the end, the message is that muon collider results can lead to joint WIMP discoveries with direct and indirect detection. So if we go beyond the very minimal models, and we go towards more simple models of dark matter mediator, well, you have the standard model mediator where you have the Higgs portals. We'll see more resulting context later. But you can also have a beyond the standard model mediator, and vector-like, scalar-like, however you'd like. That is something that's a lot simpler from supersymmetry, but the idea is to use it as a building block for more complex models. And the reason why this has been so popular at the LHC is that if there's a force other than gravity, then there's a mediator, and colliders could also detect it via its visible decays. So in 2016 and 2015, we made the Dark Matter Forum and then the working group that set up a group of benchmarks that we're still using. But I highlight early in the title of our paper that is still going, not as a good thing. We need to move on beyond these models. They are for early LHC Run 2 searches, and whenever we look at them for future colliders, they're probably not appropriate anymore. And I will talk more about that later. But how do you search for WIMP dark matter in an X plus in a very generic way is that you look for a recoil, a visible recoil against the dark matter particles. This also happens for neutrinos for sure, whenever you have a Z jet process. And you end up having a signature that is similar to what I was describing before. You look for an excess of events with high MET over the standard model background. And the point here is that background shapes need very precise theory prediction. So this becomes not anymore a search that you can do in a bump hunt kind of way, but you need precise, you need a fit that constrains the background because your signal is so small. And in order to do that, you need theory predictions to constrain the background. You can't do it data-driven, completely data-driven. The way this looks like at the end is this is an LHC jet plus MET search where you have on the y-axis you have the dark matter particle mass. On the x-axis you have the Z boson, the new Z boson mass, the Z prime mass, and then you have some hypotheses for the other parameters of the model that you have to fix. So the strength on the interaction, and here we generally fix it at 0.25 or order 1 anyway. You can also make different interpretations, and you see that structure there that is due to you have this line here where you run out of energy to produce the mediator, and this is the on-shell off-shell transition for the production of dark matter, where at the moment the sensitivity for off-shell kind of production of dark matter is not very high, but it changes in future colliders. And this is the dark matter interpretation of the jet plus MET search in FCCHH, where you see I think this is informative because it shows the level of, this is with uncertainties that are pre-fit. You see the level of the signal and the level of background, and this is a logarithmic scale. So this is the kind of thing that one is dealing with. Of course, you are on the tails, so it's a bit easier, but it's not that much easier. And this is why you need precision information on NLO corrections for the main backgrounds and pardon distribution functions especially. And these two things, the prospects, were covered in the talk by Stefan on Tuesday. So here, these are studies that by some are considered quite aggressive, I would say, but it's in the end, this technique is exactly the same that we're using now. And one can also estimate the uncertainties on this, but this is what happens to your kind of triangle of the previous page for future colliders. There's a lot more sensitivity to the off-shell region, and you can, basically this is, you stop producing the mediator at, I don't know, 5, 10 TeV. In this, no, actually 10 TeV is here. So it's something that is about 5 TeV, depending on this is the LHC, Halloumi LHC, and then you get to the 10 TeV scale if you go for an FCC at 100 GeV. And if you put things in context, then you can forget for the green part for a moment. This is still a region where you could discover something that does make up the relic density in this particular model. There's also parallel between the dijet searches that I talked about and the invisible searches, because if you detect invisible particle from a mediator, that mediator must have been created by quarks. And at that point, you can also decay the mediator into quarks. The signal is still rare and the background is still very frequent, but you have a parallel signature in hadronic decays. And there's complementarity between the searches that look for a bump and searches that look for an excessive missing transfer momentum. So just as an example, this is how the two plots, the constraints from the two searches match each other. So you have the structure of the plot that we've seen before, dark matter particle mass on the y-axis and mediator mass on the x-axis, and you have the direct search for dark matter particles like this triangle because of the on-shell off-shell transition. And then for when you add the dijet constraints, assuming that this is just a leptophobic kind of resonance, the dark matter mass at that point is not too relevant, especially when the decays into quarks dominate. They're much smaller. So it's possible, makes it possible for colliders to constrain the parameter space, even if dark matter is too heavy to be produced at the LHC. But this doesn't go the other way. So you can't discover dark matter if the dark matter is too heavy. You just don't see it. You can, however, constrain it. And in any case, you need the connection between dijet discovery and dark matter discovery. even if we see an invisible particle at the LHC, we are not going to be able to say that it is the dark matter, because we've not seen cosmological evidence at the LHC we produced it. So there's an uncovered region, and this is again not uncovered anymore, but it was when we started this kind of business of complementarity between visible and invisible searches. And it's part of the challenges that of recreating dark matter and dark sectors in the lab. You want to stay as model agnostic as possible. It's interesting to exploit what the LHC is good at, focusing the presence of a resonance. And we know how to do the resonance searches. The problem is that these kind of processes are very rare, and many other processes look the same, so you have huge backgrounds, and often you don't know how the resonance decays look like. So it could be a dijet resonance, but it could be a weird dijet resonance, and we discard it. And this is part of the big science aspect of future colliders, especially hadron colliders, that we have too much data. And we have looking for rare signals over a sea of similar looking and much larger backgrounds. So the problem is really that recording all the LHC data even takes 400,000 petabytes per year, just with the numbers that we have. And that's not a size that we can actually sustain with the current storage. FCC-HH plans to collide beams up to every 5 nanoseconds. At the moment, it's colliding every 25 nanoseconds. So this problem is not going to go away. And what we have in terms of technology, so for example, Moore's law for chips that lead to how much computing power you can get, and also storage cost, don't scale as fast as that yet. So you also have other experimental requirements, but this is the one I'm focusing on. And this is something that we generally solve with trigger. We select interesting events in real time, and we discard the majority of it. So we go from 30 megahertz of collisions to 1 kilohertz of things that we can get in our data sets to analyze. And this is a very hard cut. And the problem here is that we might be missing rare hadronic processes, because if you have your signal at very high masses, then everything is fine because you're recording all the events there. But what you're discarding is actually the majority of QCD at the low masses, and probably also your signal. So the lack of full data set, the impossibility to record all events in full harms your sensitivity, because you're going to have weighted events with a very large weight. Sure, you can reproduce the distribution, but then your sensitivity is gone. And then this is something that a number of people, theory, experiment, and so on, found out around 2013. Selecting interesting events works for most of the LHC physics program, but it's not optimal for rare processes with high rate background, because we're discarding both background and signal. So if you're looking at low mass dark matter mediators decaying to dijets, there's a large unexplored part of the phase space in dark matter mass mediator mass scenario, where you could still make a model produce the right amount of relic, but you can't get to it because you don't have the triggers to do it. So this is why others and myself have been advocating a paradigm change for collider experiments that go from asynchronous data analysis, where you first record and store the data and then reconstruct and analyze it, onto real-time data analysis. So use the trigger to do the data analysis. It's already reconstructing something to make a decision. So at that point, you can record only smaller final state information. And this is something that has been done in the CMS and LHCb first, and then also in Atlas. And the idea is that you have these two levels of the trigger, in which you have a fixed amount of bandwidth coming out at each stage. And you can either store a large amount of data for a small number of events, or a small amount of data for a lot of events. So this is something that you either perform as much analysis as possible in real time, so reconstruct, calibrate, pre-select, and then get a small amount of data, and keep the final trigger objects only, drop the raw data to make the event smaller. Or if you're interested in something that is a bit more complex in terms of signatures, you can always save the interesting parts of the detector. And this is the implementation. I'll just skip this. So I think I want to stay within the hour with the talk, and I have quite a bit to go through. But anyway, this is just a picture of how much smaller this event, the event we call the trigger level analysis event, is compared to the full event. And it allows us to see to record a much higher rate of events. So the blue is what we record, and the orange with this method, and the orange is what is recorded with the regular regular methods. And this means that you can fill the uncovered parameter of low mass quite easily with this kind of techniques. It's the blue one. But in the future, we still want to keep looking at electroweak scale couplings of digit resonances. Maybe this is a lost cause, but I like lost causes. It's not something that I would like to give up at any future collider. And we have to also work on the theory side of things, because doing a bump hunt is not just about taking data, it's also about understanding what the background is. But it's something that I think it's this kind of techniques will be necessary, I think, at the future collider and future colliders, especially hadron colliders, and not only for digit resonances. You also might have noticed that the definitions of low mass and light varies depending on what community you're talking about. For me, a collider physicist in digit search, the electroweak scale is low mass. On the other hand, this is the kind of same mediator that you connect to less explored, lighter GeV scale mediators of dark matter. And there's a lot of other literature and reviews on feebly coupled mediators and displaced mediators. Here I'm just talking about the most common mediator-like particle that is a dark photon. So it's basically a vector particle that can decay either visibly or invisibly, but here the decay rates are fixed depending on the mass. So it's a more constrained theory. And here, if you assume that your dark photon decays into leptons or into muons in this case, in hadron colliders, there's the same problem as digit searches at masses below the Z. So the reason why there's a lot of experiments that are not collider experiments that can reach the lower masses, but this kind of place here between 10 and 10 GeV and 1 TeV, this is a special place where future colliders can give inputs. But at the moment, the projections that we're using assume trigger thresholds like the Lhc21. That is not necessarily something that it's not reasonable to do that at FCCHH. So it's important to keep in mind these non-standard analysis workflows to make the most of future collider data. Now onto something that is a bit stronger. Strong dark interactions, so not just the WIMP interactions, mean that we're going to get non-standard collider jets. So the idea here is that we want to go beyond the low-hanging fruit. We've searched for digit resonances. On the other hand, that nature making our jets weird and QCD may make them invisible to our digit searches or semi-visible to our digit searches, depending on what model you're looking at. So there's a whole class of dark sector models, of which some include dark matter candidates with uncovered territory. And they include dark works that can fragment in a QCD-like way, so dark QCD. And the current signals are actually limited by trigger rates because we look for things that are above the TeV. And there's a lot of work being done here, and I think it's interesting in the context of the ECT STAR program, that is, do we understand QCD well enough to actually find these new particles, this family of signatures? Mapping is not easy because it's very difficult to prioritize on theory grounds. So it's difficult to decide what exactly to save and select in advance. So the solution is take everything and then analyze it later. So this is something that we're going to try and do already at run 3. So save a mixture of trigger level objects and raw data in interesting regions so that we'll make sure that we also have the information about the substructure of this dark shower. And there's a research program starting where there's interesting benchmarks. And I think this is the reasons why it's interesting to understand them is that we're forced to use to understand QCD better, because who knows if that is a dark shower with a dark matter event in, or it's some fragmentation we haven't really pinned down yet, and how hard is it to do that? I think the role of measurements, for example, with the contour program will help us narrow down the parameter space at least, because there's plenty to be explored. And this is one place where we need a stronger connection between theory generators and different experiments, because you can look at dark sector particles in jet and look for those specifically in precision experiments, but also as with weird jets as a whole in hadron collider experiments, for example. And I will have to skip this one. It's the work that has been done on dark showers, but you can go back to the talk. And then finally, the last 5 minutes, I wanted to talk about synergies and complementarities for future BSM searches. And it's controversial maybe to some, but I claim that colliders cannot discover every or any even kind of dark matter by themselves. The obvious reason is that there's dark matter models that are not accessible at accelerator energies or intensities. And the second reason is that you need a complementary experiment that involves dark matter with cosmological origin. Because direct detection, for example, can discover dark matter interacts inside the detector coming from space. And indirect detection can see annihilating or decaying dark matter. On the other hand, we shouldn't discount the role of colliders in this picture, because accelerators and colliders can probe the dark interaction. As I said before, you don't really have any information about what's happening with the mediator if you have a low energy interaction, and colliders can do that. So you can put things together, but you have to do it in the context of a model. So this was the European strategy update big question, where we tried to specify fully the model parameters and be aware of limitations. So we performed comparisons within chosen model, benchmark models and parameters. And you see below here that we are using actually still couplings of order 1. And you can make plots like this, where you have direct detection, indirect detection in the future with the Higgs bosonous mediator, or you have comparison of indirect detection experiments, that are these ones, with the future collider experiments for a generic scalar mediator. And the message, the only message that I think you can claim you can take out of this plot is that you want to be, you really wish for dark matter to be in a region, to be found in a region where you have more than one experiment at the same time. And this is again a model, a message that is limited for different in the limited space of a benchmark model. One cannot use these plots to say, in the next 50 years, we will exclude dark matter, or technique A is better than technique B. So I think these are very nice plots to see because they give one message, but that message is tricky to interpret sometimes. And the ongoing work is to extend these early LHC benchmarks to lower masses and couplings, because we could extend these plots to dark matter mass below 1 GeV. But we have to think about the possibility of problems in the theory and nuclear physics that we use for the conversion. But I think I'm still keen to do this if we can go for couplings of order less than 1, because couplings of order 1 may paint a misleading picture and say, well, given that we have the LHC or whatever that's already excluding all this dark matter parameter space below 1 GeV, then who cares about direct detection anymore? WIMP is excluded, and this is really the bad message to give. There's also a possibility of complementarity plots to be made linking lower and higher energy scales, and we're talking here about accelerator experiments or tabletop experiments and high energy colliders. So you have a coupling related quantity on the y-axis and a ratio between the mediator mass and the dark matter particle mass on the x-axis, and you see that here there's high energy colliders that take over at higher ratios, and then the other experiments are more dominant at lower values of this ratio. And then I'll skip this as well. So this is how, in practice, we want to extend the models to lower masses and couplings. But there's also been an evolution in dark matter searches in the last decade that we must, as collider physicists, be curious about. We used to have the trinity of dark matter searches: direct detection, indirect detection, and colliders, but now we have neutrinos, quantum sensors, accelerators, astrophysics, gravitational waves, and so on. And this is something that we really need to discuss, because the risk is that we end up being in conflict rather than in synergy. And this is something we're trying to do in SNOMAS, where we're trying to think about together new ideas that can be implemented on short time scales and can give results on short time scales of certain models, but also in light of the future colliders on a much longer time scale, or even generation 2, the direct detection experiments. And if you want to join these kind of discussions, then there's a few links there. There's also complementary projects going on in Europe as a consequence of the European strategy that have to do with the searches and the interpretation. So this is an expression of interest, the joint ECFA, NUPEC, and APEC activities. So it's the accelerator community, the astrophysics community, and nuclear physics community that join together. And we're trying to put together a platform and tools to facilitate collaborations of existing groups on dark matter searches and interpretation. We had a kickoff meeting in May, unfortunately also in online. but that's what it is. And hopefully next year we can have an in-person meeting in the spring. And another thing that I'm keen on is working on the software and the data. And this is done in another European project called Escape, where we compare end-to-end analysis workflows for WIMP searches. And we can implement them in a common software catalog and give it an input to the design of the European Open Science Cloud. And this is now hiring a few postdocs for this purpose. So finally, I'll conclude. Sorry, I had to go a bit fast on this, but I got carried away with this. Is a lot of things I love talking about. So first message is, what does it take for discovery? I talked a lot about real-time analysis, but that's not real-time we need for discoveries. We need time. And we aren't done taking LHC data. We have 10 times more expected at the Halloumi. So we checked the low-hanging fruit, but we can expect surprises. And as written also in the European strategy update, real-time analysis and decision-making, but also every other kind of thing that you can talk about in technology, computing, big questions, crosses fields. So we have to go beyond the large collaborations as experimentalists, because we have a microcosm there. And it's great to talk to our colleagues. And maybe we have too many meetings also. That's the reason why a lot of people maybe don't attend the full workshop. But we have to be curious about what other fields and other people are doing, because we can really learn from that. And we can collaborate on tools and infrastructure. I think this is the time in which to search everywhere, including for the rare and unusual. This is not the time to say, okay, we're done working on Exotica, especially in light of the complementarity between colliders and other experiments. For example, that you have in dark matter, but it's there in many other places, as this again was Julia's talk. You have in dark matter, you have cosmological origin and nature of the dark matter standard model interaction that is fully complementary. But there's also a complementarity in tools, given the shared theory and experimental and computing challenges. So I encourage everyone to just look out and work together. And thank you for your attention.
Thank you very much. So thank you for this nice and comprehensive talk. Are there questions? You can raise your hand or also just speak. Okay, maybe people are a bit shy to start. So let me ask maybe generic question from Theo's point of view, but as you are an expert, you were talking about trigger level analysis. And well, that's extremely interesting, and also obviously somehow something which is unavoidable in the future and already in the present. And I was curious about how flexible or adaptable in time are these trigger level implementations, because okay, suppose that at some point you work at Collider, but you have some hints coming from elsewhere and you want to change a bit your trigger strategies. Is it possible? How fast can that be done?
I think this depends experiment by experiment, but the best example of a very flexible system is LHCb, where it's basically the user that decides, and they understood very well the trade-off between, I want this with very high precision, but I'm going to get less data, or I want this with less precision, but I'm going to get a lot of data. So this is one aspect that one can change this, I wouldn't say on the fly, but over the course of one or two runs, you can actually change this. For Atlas and CMS, because there's more emphasis on the recording in full so far, it's a little bit harder to change things. On the other hand, we all think about what happens if you have a discovery in a trigger level analysis. You need to know more about it. So there are trigger lines in pretty much all cases that can complement. If you see an excess in a trigger level analysis, you can turn on a corresponding trigger line that will give you the full event in that sense. And if you see an excess, it's going to be done quite fast, I think. There's also another possibility I didn't talk about, but I think CMS did it in the past. I don't know if it can do it in run 3 as well, that you park the data. And we did it in Atlas as well for a good part of the data set. So in parallel to the trigger level analysis data, you also have the full stream, but you don't reconstruct it right away. It's a little bit less, it's a little bit less data, because the problem is storage in the end. But you can solve the I don't have enough CPU for reconstruction problem with that technique. So you can also put it away and then look at it later if there is a discovery.
Okay, thank you. I see that Roberto has a question. Please go ahead.
So I was saying one aspect that at least I think is very important of these collider searches is that to an extent you can be sure of the conclusion, positive or negative. You reminded that the 750 diphoton excess, it may last a little while, but at the end, you know how it ends. You know, you're sure it's a statistical fluctuation. You said that. On the other hand, you mentioned a few things that are in a way not so sure. And for instance, this G-2 that you mentioned, and that eventually maybe a muon collider can thoroughly check and give us you know, a definite answer, I would say. So I wanted to know what is what's your take as an experimentalist in pushing for these very high precision measurements, which recently we are learning they are not supported by enough theoretical precision. So this is also seen in future projections for future colliders. We like to go this way, but I'm wondering myself, for instance, if we should learn a lesson that not everything can be computed at arbitrary precision eventually. And in the meantime, we keep doing experiments which are inconclusive for this reason, even in the collider realm, okay, where we like to have conclusions of sort. And on the other hand, I want to say, for this complementarity you mentioned of dark matter discovery, for instance, I would definitely push for a collider probe of these things, because the day you find anything in direct detection experiments, I will not believe it until I see it in a collider. I'm sorry, but I mean, we know how many anomalies are existing already in that plot, and indirect detection as well has its own problems. So I don't want to give the impression that I'm negative on colliders and this kind of experiments, but I wanted to hear your opinion on this, I would say, rather prevalent these days approach of going for super precise things, and which we will hear also this afternoon, I think. And then theories is given for granted, but I think right now there is experimental data, quote unquote, that's not always the case. So what do you think about it?
It's a complex question, I think, in the end, because it's a matter of how one distributes resources ultimately. Even in the collider scheme, you can ask, why are people not doing enough measurements? And there's so many things that you can measure, and maybe there's a lot more people that are looking for model A of supersymmetry or model B of exotica. Anyway, I think to conclude what I was saying, I think it's that if we manage to reconcile searches and measurements as part of the same thing, then it will be also easier to engage the theory community. And at that point, we will be able to, rather than maybe have definite questions, at least go hand in hand, because experimental uncertainties are not small. And a lot of the time we do things that maybe are not proper to get the uncertainties done. Like I'm talking about 2-point systematics and things that then we end up putting in fits that maybe we shouldn't be doing. So more discussion about that will allow us at least to go to proceed at the same pace, and possibly not solve, but help the problem that you were mentioning. I hope this answers your question.
I'm not sure if I'm still there. So
I think it's
lost connection probably.
It looks like it doesn't have he's there, but the microphone or the camera is not there anymore.
Okay, in any case, thank you for this explanation. I have another question because I was not aware of the snow mass discussions you were mentioning on the possibilities of, let's say, non-collider probes and the time scale for those. So basically, I guess you have discussed this in detail. Is there an outcome? Is it clear if there is any winner, or there are more winners, or what is expected to gain data, or at least put limits first in the next decades?
You're talking about dark matter here.
Yeah, sure. Dark matter.
Yeah. So I think this is a question that we just started exploring in was it like November, December last year, but then SNOMAS paused. So it just went, there were too much going on, COVID, the number of sociological and social problems in the US. People felt that it was better to just pause for a year and then resume. So we're resuming that discussion now. But I think the way we're trying to portray it, and I can show some sketches that are also kind of fun. There's like mountains and skiers and that's it's trying to say that we're approaching the problem from different directions. So you can't really say this is the winner. Of course, if you build an experiment that looks for one single model and that model is one point in parameter space, you target it specifically, then that experiment will be the winner of that model. But that's not telling us very much about the full picture. So we're trying, and it's going to be very, very difficult, and it possibly takes a lot of energy because there is the tendency of wanting to say, for funding reasons, I will be the first to discover this thing. And it's easy to understand why this is the point. But is this the way we want to go, or do we want to give a more nuanced approach and then let someone else maybe prioritize? I want to find this thing first, so I prioritize this line of experiments. So I want to find this other thing first. And that will be, it really is a matter of giving a balanced view rather than a view that makes a plot that makes one experiment look better than the other. It's not easy. But yeah, it's an interesting question, and we're trying. We're going to restart, I think, in the next few weeks. We're starting the discussions.